can see me, and anybody who wants to join the Hangout, either to ask me questions or just to see what's being asked, can do that too. It's up to you. If you don't want to use that, that's fine. We'll see how it goes for a few weeks and either keep doing it or toss it out entirely. It is a little bit weird. All right, any questions about last class, assignment, anything? Yeah?
For part 7 of the assignment, the one where it has to find the biggest number and then the biggest one after that.
Yeah.
Are you going to be testing any cases that don't use numbers?
Yes. Yes. It's not. Don't. The only reason I use numbers in the examples is because it's really easy for us to look at two numbers and say which one is bigger and which one is smaller. When I use letters, sort of strings in the examples, we already have difficulty ordering the alphabet. You know, I and H. You have to think for a second to see which one comes first, unlike numbers. Yeah, so that'll be lexicographic order on strings. So if you notice, even if all of your strings are just integers, that's still not the same thing. Because, for example, in lexicographic order, 88 comes before 9. So it's really strings. All the examples, I just use one-digit numbers, so that makes it easy. Any other questions? How's it going with the assignment submission server? Are you happy so far? Yes. Does it feel good to have some idea of whether you're doing this right or not? Okay, that's good. That's the hope. So you guys who are doing it early are happy with it. My guess is there will be a bunch of other people who start really late and are not so happy with it. So don't be one of those people. All right. So last class we had looked at what in the textbook is called array stack. And it's basically a clone of what in the Java collections framework is called array list. So, you know, the question is, well, why does the Java collections framework call it an array list and I call it an array stack in the textbook? Well, that's because I want to highlight the fact that this data structure is fast if you use it as a stack. So remember, everything lives in an array. 0 up to n minus 1. And when I say it's fast if you use it as a stack, I mean it's fast if you add things at the end and you remove things from the end. If you do other operations, adding and removing from the middle and so on, or from the front, then that's not so fast. And so the name of the implementation reflects that. It is still a list implementation, and it's a list implemented as an array, but it's not the only way to implement a list as an array. This name just kind of reminds you that, yeah, okay, it implements the full set of list operations, but kind of use it like a stack. Just push things on the end and pop things off the end. Don't try and do other stuff, or else it's going to be slow. And we looked at the implementation, and we did a very quick test. I'll run another very quick test against the array list implementation in the Java collections framework. So here's a very quick test, adding 1 million elements to the end of one of these things. If you use an array list, that's this number up here, takes 0.06 seconds. Using an array, our implementation of array stack takes 0.04. And then we have this thing that's called a fast array stack, which takes 0.06 seconds. First thing I'll tell you is that in Java, these numbers are pretty much meaningless. Does anybody know why that is? So when the numbers are this close together, 0.04, 0.06, anyone know why that's not really important information in Java? Yeah?
It also varies, like runtime.
So runtimes tend to vary wildly in Java, and that's because Java is what's called a garbage collected language. So whenever the Java interpreter is running low on memory, it pauses execution of things and runs around looking for objects that are not being used anymore. This thing called the garbage collector runs around looking for objects that are not being used anymore and gives them back to the free pool of memory that can be used. That's a slow process. You're never quite sure when it's going to happen. And for instance, maybe the reason that these two were slower than this one is because the garbage collector ran more in the first one and the third one, but not in the middle one. If you're ever curious about that, you can actually ask Java to show you when the garbage collector runs. So we'll pause that. So here we see, while we were making this array list, this thing told us that the garbage collector ran. So an allocation failure means it was unable to allocate some memory. That invokes the garbage collector to go clean up some other resources to find that memory. So it actually executed during the first one when we were doing the array list. On the array stack implementation, the garbage collector didn't have to run. So it got lucky that time to do the garbage collection didn't count in the running time for that thing. And the fast array stack implementation also had one of these allocation failures, so the garbage collector ran there. So you have to be really careful when you're comparing Java implementations and you're measuring fine things like small constants in the running time. You might be really happy with, with something like these results here and say, oh, look at my implementation is nearly twice as fast as this implementation, but that's just a function of when the garbage collector happened to run. You could probably change that just by changing the order in which you run these two tests. So there's some stuff to look out for there. If the two have running times that are in the same ballpark, then that's, without investigating carefully what the garbage collector is doing, then all you can say is they're close. So there's array list, which comes from the Java Collections Framework, array stack, and then this thing that I call a fast array stack. What's the difference between an array stack and a fast array stack? The only difference is when we design this array stack, there's all this shifting and copying that happens. When you allocate a new array, you do some copying. When you insert into an array stack, let's say in the middle or near the front, a whole bunch of shifting has to happen. We implemented all of that with for loops. So here's an example of in a resize when we copy the array A onto the array B. Here is an example of when we add something and we do this shifting, we use a for loop for that. It turns out that if you're going to be doing that kind of shuffling things around in an array like that, which is basically moving big chunks of memory, then Java and almost every language has special system calls for that. In Java, it's system.arrayCopy. So you tell it the target array, in this case A, the target index, in this case 0, the source array, the source index, the target array, the target index, and the number of elements you want to copy. And then this goes off to some fast native operation that does this as fast as possible. It's not just a for loop that's copying one element at a time. More likely, it's using some processor instructions that can do things like copy 4 elements at a time in the time it normally takes to copy 1. So system.arrayCopy is generally faster than a for loop that's doing the same thing. That's the only difference between fast array stack and array stack. And you don't see, in these tests, you don't see such a huge difference. So what are the things we do? We do this add operation, and roughly the running times are the same for all our implementations. That's just appending to the end of the list. And the differences in running times are due to garbage collection. This remove operation, so on an array list, and on an array stack, and on an array stack, and on a fast array stack, So these two seem to be a little bit slower than an array list, maybe twice as slow. That could be due to garbage collection, but that's unlikely because the Java garbage collector is a bit lazy. It only likes to collect garbage when it needs to. That means you're running out of memory. When we're removing things from one of these data structures, there's no extra memory needed, so the garbage collector is probably not running. And we see that the array list seems to be actually quite a bit faster, more than twice as fast as array stack and nearly twice as fast as this fast array stack. Anybody guess why that would happen? Yeah.
Where are you removing things from?
We're removing from the end. So we want to look at the code for that. We have this append test. It's right at the end, Q test. The remove test, basically, as long as the thing is not empty, it removes from the end. So it's doing the same tests for all three implementations. Any guess as to why? Yeah. Yeah, we skip that actually, so we should be faster in that sense. They don't. Yeah.
Maybe it downsize the array list?
Well, that's the thing. They cheated. I noticed that this was happening consistently, so I looked it up, and I mean, you remember that when we do a removal, when the array gets too empty, when it's only a third full or so, we resize it so that it doesn't stay huge. It stays roughly this, twice as big as the number of elements we're storing in it. So I looked up the source code for the Java ArrayList implementation, and I looked up remove. So here, removing an index. And it does, it looks like more or less the same things. There's a range check function, which just asks if the index is too big. There's this mod count function, which it uses to, I shouldn't have clicked that. It uses to check if you are trying to modify something while something's iterating over it. It's not something we worry about, but let's get back to remove. So it increases this mod count. That's just to help it complain if you're using an iterator and you change the list. It saves the old value. That's what we did. It figures out how many elements you have to move. Then it uses system.arrayCopy to shift those elements over. It decreases the size. Oh, stop. It decreases the size and sets the last value to null and returns the old value. Notice what's missing there. There's no checking to see if the array stack is getting really empty or not. It just will happily create an array list that has, 1 billion elements, and then you reduce that number down to 5 elements. There's still a backing array there of size 1 billion. It never tries to give you back that memory. So they cheat in the sense that the only way to remove, it doesn't resize this array to make it small again. So something to know if you're going to use this thing and you're worried about memory. Okay, so having said all that, so they can do remove a bit faster because they never try and make the array smaller. We add a bunch of elements again. We do a bunch of get and set operations. Let's run this test from the beginning again so we can see. We do a bunch of get and set operations. What do those do? All they do is pick a speed test. All they do is flip a coin to decide whether you're going to get or set a value, and then they pick a random index and they either get it or they set it. If we look at the performance of those, 0.05 seconds for array list, 0.05 for array stack, 0.099 for fast array stack. That's probably a garbage collection issue, unclear. But all reasonably fast. If we do stack operations, meaning that we add and remove from the end of this thing, so let's take a look at the code for that. Stack operations, you toss a coin. If the coin comes up heads and the list is not empty, you remove the last element. If the coin comes up tails, you add an element to this thing. Then those are also very fast. We can do 1 million of those in 0.89, 0.02, 0.02, and the 0.89 is probably a garbage collection issue. That probably closer to 0.02 for all three implementations. And then finally, we try and do queue operations. What are queue operations? Well, a queue, remember, adds things at one end and removes things from the other. So in this case, we do this by tossing a coin. If the coin comes up heads, we remove the 0th element. If the coin comes up tails, we append something to the end of the array. And we see here that the queue operations are still running. So the other ones finish, in fractions of a second or, 20ths of a second. This one hasn't even finished for the first implementation yet. So that's slow. What part of that is slow? Is it the remove operation in this code, or is it the add operation that's taking so long? Yeah, go ahead. Someone said it, but I didn't see them. Yeah. It's removing from the beginning, and remember, when I remove the 0th element, something from the beginning, everything else shifts over by one position. And so that's really slow. When you have an array stack with 1 million elements or an array list with 1 million elements, that means each remove is causing 1 million things to get copied. And you try and do that 1 million times, and it takes a while. So that's what's happening here. So queue operations are not well supported by this thing, and that's why I call this thing an array stack and not an array queue. So now some of you know a little bit maybe in advance, or maybe you've seen it in earlier courses. You would say, well, in that case, you shouldn't be using an array-based data structure for this. You should use a linked list if you want to have a queue, because linked lists are nice. You can easily remove from either end. But actually, today we'll talk about how you implement queues and even decks using arrays and do it in an efficient way. So what we want to do is be able to somehow represent a list in such a way that we can do operations either at the front of the list quickly, or we can do operations at the end of the list quickly. Okay? And what have we learned so far? Well, we have one tool in our toolbox, and that's the lesson that we learned from array stacks. And the lesson we learned from array stacks is that, and we actually started to, this is how we presented array stacks, is we began by pretending. So we pretend we have arrays that can grow or shrink when we need them to. I mean, that was the main lesson from last class, is that in an array list, we have this backing array, and as long as we're careful with it, we can just pretend that that thing grows when it needs to, and it shrinks when it gets smaller. That was this resize operation that we implemented. And after we used that, ignoring the fact that we had no idea how to do it, or at least do it efficiently until that point, what we learned is that we can actually implement this with, let's say almost no extra cost in terms of running time. We saw that with this strategy that always makes the array twice as big as necessary. If you do it when it's full, you make it twice as big as necessary. And when it's only 1/3 full, you again make it twice as big as necessary. That actually that doesn't cost much. In that all that growing and shrinking that happens behind the scenes doesn't add up to more than the number of add and remove operations that you do. More than twice the number of those things. Okay? So this is a common trick when you're designing data structures, is to imagine something that makes your life easier, design a data structure having, in a world where that thing exists, in this case, arrays that grow or shrink when we need them to make our lives easier, and then worry about how you implement that after. So that's what we're going to do here. And what we're going to pretend is something even better than arrays that grow and shrink. We're going to pretend we have infinitely long arrays. And not only are they infinitely long, but that extend from minus infinity all the way up to plus infinity. So what does that look like? That's an array that looks like this. Here is index 0, index 1, index 2, and this goes all the way off to index plus infinity. Then you have index minus 1, index minus 2, all the way down to minus infinity. So it's certainly true that we don't have this in a real computer. We don't have infinite arrays. We don't have infinite amounts of memory in our computer, and this indexing from minus infinity to plus infinity also seems a bit fishy. But let's pretend we have that for now. And let's say we want to implement something really simple, like a queue. So a first in, first out queue. So in a first in, first out queue, that's this thing that looks like this. Imagine it's this tube. You, let's say, you enqueue at this end, or if you like to use the Java terminology, you add things at this end, and you dequeue from this end, or in the Java language, that's removing things. That's the thing that we tried to implement up there using an array stack, and we failed because this dequeuing operation was too expensive. Removing from the front is just too slow. Okay, now, what if we have this nice infinite array to work with? Can we make that work for us? So I want to implement a queue using an infinite array like this. So any suggestions? So I have this infinite array A. In an array stack, what else did we have? We had two variables that implement the array stack. The array A and what else? Yep.
Size?
The size. So the value n, which is the number of elements that are stored in the list, or in this case, the queue. So n is the number of elements in the queue. So if we look at this thing, it's going to have some elements, and then emptiness, just a void off in all directions, and it's going to have n of these things. Now, since we're implementing a queue, is there anything else we could store that might be helpful? Yep. A head and a tail. So a head means, let's say, the index of the first element. Yeah, let's say, so this thing here. So let's call that, I might as well use the same variable name that the code uses. That is a J. So let's call that thing J. Okay? So that's my representation. I have an infinite array, A. The first element in the queue, the one that we would be removing next, is stored at position J. The other elements are stored at positions J plus 1, J plus 2, J plus 3, and so on. And we don't have to bother keeping track of the tail because we know where that is. That's just J plus n minus 1. Okay. So we don't need an extra variable for that. All right. So two operations I want to support. Add and remove. Adding something at this end. How does that work? Yep. Yep. So the add operation in this case is just going to write a new value x here. So we say a at j plus n equals x. So now x is written there. What else do we need to do? Of n by 1. We just added an element. So we increase the value of n by 1. So then our implicit tail is updated because we increased n by 1, so j plus n minus 1 also increased by 1. Okay? That's the whole procedure for adding something to the end of this thing. All right. And how about the remove operation? So remove doesn't take any arguments. You don't get to say what gets removed in a queue. It's just the first element. So what does the code for that look like? Yep.
N minus minus and return a at j plus n plus 1.
Okay. N minus minus is going to be one less element. And you say return a at what?
J plus n plus 1.
Well, where's j plus n pointing to? Or
Oh, yeah. Oh, we're doing from the j.
we want to remove from over here.
Oh, okay. So then. So.
Yep. Maybe.
Plus 1 as well.
Okay. So let's do it slowly. Save whatever it is we're trying to return. A at j is what we're supposed to return. Increase j by 1. So we save this value, we increase j by 1. That means this thing points to there. And we'd better decrease the value of n by 1. Otherwise, this thing will point past the end of this array. So the number of elements has decreased by 1. And if we like, we can also set, if we want to be nice to the garbage collector, we can say a at j equals null to free that thing. Okay? So that wipes this out, effectively removing the first element from the list, and returns the value that we removed. Nice and easy, right? Okay. So what's the, it looks easy. I mean, this looks great. I don't see any problems here. The only thing that we're missing is this implementation of this infinitely long array that can grow in either direction. In fact, I don't think it's hard if we wanted to, not just implement a queue, but also be able to add at this end and remove from this end. I don't think you guys, most of you, would have much difficulty writing down the code for that, right? It's just a question of, when you're working at this end, you manipulate n, you write something to that end and increase the value of n, or you decrease the value of n. And when you're working at this end, you manipulate j and n. So you have to decrease the value of j and increase n, or increase j and decrease n, either way. Okay. But that all assumes that you have this infinitely long array. Okay. So how do we implement an infinitely long array? Well, I don't know. You can't really do that. What I do know is I can implement arrays that grow when I need them to. That's using the trick that we learned last class. And I can also combine that with another trick, which is implementing arrays that effectively are cyclic. So we usually think of an array as a bunch of boxes all lined up in a row. Now let's take that line of boxes and bend it so that its two ends meet each other. So remember, these are index 0, 1, 2, 3, 4 up, all the way up to n minus 1. And we can actually say, well, we'll do more than that. I'll keep walking around this thing. So I count up to n minus 1 and keep walking around. And this position here, not only is it called 0, I'll also call it n. And this one, I'll call it n plus 1. And this one, I'll call n plus 2. This one, I'll call n plus 3, all the way around there until here I have 2n minus 1, and then up to here, 2n plus 1. I can call these things by any of those names. So give me array index n, gives me the same thing as array index 0. Give me array index n plus 3, it's the same thing as index 3, 2n plus 3, 4n plus 3, and so on. And you can even extend that in the other direction, starting at 0 and counting backwards. You can call this thing array index minus 1, array index minus 2, minus 3, minus 4, minus 5, minus 6, down to, this would be minus n. Okay. And then here, minus n minus 1, minus n minus 2, and so on. Okay. So imagine we had this kind of array that's in a circle like this. There's no indexing out of bounds. Any index you give me will give me a value. a position in the array. It's just that every position in the array has a whole bunch of different names that you can call it. The most common name is an index between 0 and n minus 1, but add any multiple of n to that and you get the same position in the array. So mathematically, what do we use to implement this? Yep. Yeah. So what we use is what's called modular arithmetic. And this is, you know, I think they try and teach this in grade schools. They call it clock arithmetic, where, like clocks, you know, after what follows 12 o'clock or what follows 2300 hours is 0 hours, 100 hours, and so on. So, I mean, think of these as the numbers on a clock in maybe 24-hour format. Then, indeed, as you count around these things, it just wraps around this way. So, if it's 3 o'clock right now, what time will it be exactly 3 days from now? Well, it's going to be 3 o'clock again. So that's what they call this. They like to call it clock arithmetic. But a little bit more formally, if you take A mod n, so this is the modulus operator, this gives you a number. So it takes any integer a and it gives you a number between 0 and n minus 1 such that a equals k times n plus r. So a mod n is equal to the unique value r in 0 through n minus 1 such that you can write a as some integer multiple of n plus this remainder r. Another way to think of it is you take a and you divide it by n. So you do integer division. There's some remainder. That remainder is the mod, the modulus. Okay. All right. So for example, if a equals n plus 1, then indeed you have n plus 1 is equal to 1 times n plus 1. So this is the remainder. That says that, you know, n plus 1 is in the same class as 1. Okay. In programming languages, how is this usually implemented? What symbol is used? Yeah. Yeah, it's usually the percent sign for some reason. So in programming languages, you'll usually do a percent n. This is fine. A couple of things to look out for. So one of them is tends to be one of the slowest arithmetic operations you can do on a modern microprocessor. That's okay. It's not such a big deal in a language like Java. But a bigger problem is be careful with negative numbers. Because many languages just say this thing is implemented by whatever the hardware does, and the hardware, when a or n is negative, may not satisfy this definition. But as long as both numbers are positive, n is positive and a is positive, then things are okay. Okay? All right. So how is a circular array going to help us here? Well, let's see. So if we do all our indexing mod n, and we have one of these circular arrays, usually you cut them to show where the 0 starts, can we implement this thing that we're trying to do here? So what do we need? Well, we have this array A. Here it is. We have this index j, which points to some element in this array. And we have this value n that tells us how many elements are in our queue. And so what we know is that positions j plus 1, j plus 2, j plus 3, and so on, all of those things contain the elements in our queue. Now, if we want to add something to the end of the queue, it's exactly the same procedure, right? Sorry, this should be j plus n minus 1. This count of these elements is n. So if we want to add something to the end of the queue, it's exactly the same procedure. We go to array position j plus n. That's this thing here, right? We write something there, and we increase the value of n, which does that. So that's how we add to the end. And when we want to remove from the front, we go to position a plus a at j. We save it and overwrite it, and then we increment j, and we decrease n because by incrementing j we implicitly move this forward, so we move it backwards again. So this circular array is just about as good as this array that extends in either direction. If we want to, add something, go back to here. It's all nice and simple. Are we hiding anything there? Any problems? Yeah.
What happens when the full array gets like every element filled?
Yeah. So what happens when we get to a state? So the problem, and we've seen this problem before, is we have this thing that we're imagining as a circular array. And it's able to store some number of elements. The number of elements in this circular array is called a.length. And sometimes we may be, j. And sometimes we may get to a state where n is equal to a.length. So what does this picture look like then? Yep. It's just full. There's x's, there's data everywhere. This position here, this is j plus n minus 1. Okay. And now, if I try and add something either at the front or at the back, well, you see what's going to happen. If I try and add it at the back, well, then I'll try to write to position j plus n. That's this position here. There's something already there. I'll write to it, and I'll overwrite the thing that's in the front. Okay? So that's not going to work. Somehow I'll lose data here. What's worse is this is a little more insidious than the same problem on arrays, because this won't crash. This will happily overwrite this data here, but it won't crash at all. It'll just, the data's there. There's some place to write. It's not going to give you an out-of-bounds exception or anything. It'll just happily do it. You'll have an error in your program, but it's not going to crash your program immediately. But it's the same problem as when we were trying to implement a list as an array, and the array gets full. when you try and write past the end, you have a problem. But luckily, we know how to solve that problem. If we have an array, we're trying to simulate, we have this circular array. We know how to do that using modular arithmetic to treat an array like its indices are organized in this circle. And at some point, we need it to get bigger. So we use the trick that we know how to make things get bigger. When this happens, if this thing becomes full, and we still want to add one more thing, then we just allocate a whole other circular array that's twice as big. And we copy everything from this circular array into this circular array. When we do that, we can copy it wherever we want. We can start, for example, convenient thing is to take our new j equal to 0 here, start copying from here to here, to here, to here, to here, so on. How far will we get before we run out? Halfway. So we'll copy about halfway around, and then this will be j plus n minus 1. That's n items. And this guy here, we'll call it b, his length is going to be 2 times n, so that's halfway around. Okay. And now we throw away a, and we say this is your new array a that you're going to use from this point onwards. This is your new value of j. You could pick it wherever you want. j0 is a convenient place to pick it. And now you can keep going. If you want to add something, you have lots of room and lots of time to do that. Nothing different there. Just before you add something, you see if there's room to add it. If not, you call some function called resize that makes this thing twice as big as necessary. Then you know there's the space to add this new thing. And on the other side, we sometimes get into a situation where our array, our circular array, starts to get really empty, and we don't want to waste space. So we might have some circular array like this. Our j is here, and the data gets to be quite small. This is our n, and it becomes smaller than a dot length divided by 3. In which case we do exactly the same resize operation, except the result is that we get a smaller array that is half full instead of only a third full. Okay. All right. And, you may or may not have followed carefully the whole analysis of that last class. But if you believe the analysis, whether you followed it or not, then you should believe that this thing is not going to cost us much. It's basically exactly the same argument as before. That part is not something we have to worry about in great detail anymore. It's something we have in our toolbox, arrays that can get bigger or smaller. Just the only difference now is this is a circular array rather than a regular array. Okay, so that all seems rather abstract, and these circles seem weird. So let's just take a quick look at the code here. So here's the add operation. So to add an item, you do the first thing. You check if when I add one more to n, am I going to get something that's bigger than the length of my array? If so, you call resize, and you know that resize is going to make that bigger. Then you go to position j plus n, modulo the length of the array. You set that to x, increase the value of n, and return true. That's it. Right? The only thing that's different here about what we were doing for the infinite array is, well, resizing you never had to worry about in an infinite array. And we take this index j plus n and we use it modulo the length of the array. That gives us this wraparound arithmetic. Okay? Yeah. And to remove looks similar. We save the value of a at j. We increment the value of j, modulo the length of the array again. We decrease the value of n. We resize if the length of a is more than 3 times the value of n, and then we return x. And then the final thing to look at is this resize operator, which does what we expect. We create a new array B that is of size at least 1, but more generally it's of size at least 2 times n. And we copy everything from A into B. The only thing that is a little bit maybe unusual here, or that may confuse you, so we're going to copy n elements, so we need a loop that iterates over n items. We're going to start at position j in the array A, because that's where the elements in the array A start. They start at position j. And we start copying them into the array B, and we start that at position 0. Okay? So it really is this picture here. The item at position j in array A gets copied to position 0 in B. J plus 1 goes to 1 in B, and so on. And then we throw the original array A away, just keeping the big one, and then we set j equal to 0, because that is where the first item is now stored. Okay. So nothing weird. And we can write down a theorem about this. And that theorem says, it's going to look familiar to us. An array Q implements the FIFO Q interface. Then we'll have a little qualifier. Ignoring the cost of calls to resize, you have 1 add x takes constant time. So except for the resizing, all add x does is increase the value of n and write one new position in the array, and remove takes constant time. And of course, it's not really useful if that's the whole statement of the theorem, because it ignores the stuff that could be expensive. So you add a furthermore. If we start with an empty array Q, and do any sequence of M, add and remove operations so if we start with then the total time spent in calls to resize is only O of M. Okay. So this is still one of these amortized data structures with this amortized statement of the running time with the two parts. If we first ignore the cost of calls to resize, then everything else takes constant time. If we want to account for the cost of calls to resize, then we look at a whole sequence of M operations, starting with an empty data structure, and we see that the cost of all of those calls, when you add them up, is only proportional to the number of operations we've done. We don't need to prove this again, because the second part, because that's what we did last class. There's nothing different in the analysis there. Okay. Any questions? So no questions is usually worrisome for me. It either means everybody understands everything, which is well, ArrayQ, this is ArrayQ from the textbook. I think there's an ArrayQ in the Java Collections framework that does basically the same thing. But actually, the one that you should be using is from the textbook. I mean, this queue interface is fine or whatever, but really it's superfluous because the list interface lets you do everything that a queue does and more. So what I'm really interested in is the array deck, which actually implements the list interface, again from the book. So it implements the list interface, meaning that you can add or remove items anywhere. But if you add or remove near this end, it should be fast, and if you add or remove near this end, it should be fast. So like array stack, doesn't really just implement the stack interface, it implements the whole list interface, but if you use it like a stack, it'll be fast. Array deck will have the same thing. Add or remove anywhere, so just to be clear, this is the textbook implementation of array deck. Unfortunately, Java Collections Framework added their own thing called an array deck, which is not the same thing. But this is what I want, is the full list interface, where if you add, from either end, near either end, then it should be fast. If you do stuff in the middle, then I don't really guarantee that it's fast. Okay. So in an array deck, you have J, J plus n minus 1. This is the array A. So it's the same kind of layout that we just discussed. All of this, I won't write it every single time, but all of this is modulo the length of A. So the indices wrap around the ends as necessary. And the list interface has the ability to get the element at position I, which is easy enough to do. We return A at what? Yeah, A at j plus I mod A dot length. And set Ix, that's roughly A at j plus I, sorry, I rather, j plus I mod A dot length equals x. That's the short version of it. Actually, you have to save the old value and return it, but that's the main idea. And so the interesting ones are how you add things and how you remove things. So I want to implement the add operation so that it's fast if I'm adding near the front, and it's fast if I'm adding near the back. So the add operation in general, remember you give it an index I. And it is supposed to make a space here for this new thing to be added. Now, how can I make that space? Yep.
For adding, you can expand. If you're in the first half, you can shift everything over one to the left. And if you're in the second half, you can shift everything one to the right.
Yeah. So if I'm trying to add in the, let's say this is the halfway mark, so this is n over 2. If I'm trying to add something in this first half here, it makes sense, it makes more sense for me to take everything up to position I and move it one position to the left, because that's fewer elements than taking everything after position I. On the other hand, if I'm adding in the second half, it makes more sense to take everything after position I and shift it one position to the right. Okay? So the add Ix operation basically starts with a branch that says, you know, if I is less than n over 2, then shift elements 0 up to I minus 1 to the left. Otherwise, shift elements I up to n minus 1 to the right. And now that I've done that, I've made space for this new thing, so I can say A at I equals x. Okay? And then, of course, before that, you will have something like if n plus 1 is bigger than A dot length, resize. So before I can add anything, I better make sure the array is big enough. If not, I resize it. Then if I'm adding in the first half, I shift things to the left. If I'm adding in the second half, I shift things to the right. I add this thing where I need to add it, and then I do a n plus plus. Okay. So, let's see how fast this is going to be. So if I execute this line of code, or this, it's not a line of code, it's just a pseudocode that tells you what you have to do. How long does it take me to shift these elements, 0 through I minus 1, one position to the left? Yep. Nope. So how many elements are here? I elements. So shifting I elements, one position to the left, that just takes O of I time. Okay. If I end up in this line of code, how long does that take? Somebody has an answer for me already. Yeah. So I'll say, I'll just say n minus I. I'll leave out the 1. So if I end up there, it's O of n minus I time. And other than that, well, we're always going to lie about the cost of resizes anyway and worry about that later. The rest of this stuff is all constant time. So somehow, sometimes this happens and sometimes this happens. So I want to write one expression that tells me, what is the running time of this thing, this whole thing, as a function of I. Well, if this happens, then what's smaller, I or n minus I? I. And if this happens, what's smaller, I or n minus I? N minus I. So actually, this condition here is chosen so that we do whichever one of these things costs less. So actually, this whole code runs in O of 1 plus the minimum of I and n minus I time. Okay. Now, let's think about what we were shooting for. We were shooting for a list implementation that if you use it like a deck, meaning you only add or remove at one end or the other end, that it's fast. Okay? So if you're adding at the front or removing from the front, or in this case it's just adding that we've done so far. If you're adding at the front, then what's the value of I? Yep. No, if I want to add something, if I call add IX to add something at the front of a list, what value of I do I use? Yeah, I use I equals 0. In that case, this is 1 plus the minimum of 0 and n minus 1, so this is 1 plus 0. So that means if I run this with a value of I equal to 0, this is just constant time. It's just O of 1 time. On the other hand, if I call it with the value of I equal to n, then this thing becomes 0. N minus I becomes 0. And so again, this is constant time, meaning that if I append to my list, that also takes constant time. And, in between those two extremes, as I dig deeper into the list, it gets more and more expensive, where the worst thing you can do is try and insert something in the middle. Then there's no good solution. You're still moving half the elements out of the way. But if you use it like a deck, meaning you only work at the ends of it, then every operation will take constant time. Okay. Now, if we want to remove the ith element from this thing, there's no surprises anymore. What should we do? You want to remove the ith value. So remember, remove goes into this thing, position I, wipes it out, and then leaving a gap, and then closes that gap. So it shifts some elements to close the gap. So what's the first question we should ask? Yeah. That actually comes after we remove. Yeah. Yeah. So, well, I is always between 0 and n, so j doesn't actually come into it. J is just some internal thing that tells us where this array starts, where this thing starts. right? So the I is an index between 0 and n minus 1, which then translates into position j plus I in the array. So we're asking really the same question we're asking here. Is I closer to the front, or is it closer to the end of the list? And that's just asking if I is less than n over 2. So that means it's closer to the front of the list. So the picture looks like this. Here's the halfway point. I'm trying to delete this thing. So I should take these items and move them over, shift them over to fill in the gap. There's less of these items than there are items that come after it. So that is something like shift elements 0 up to I minus 1 to the right. These guys move over and fill in the gap. Otherwise, I is over here in the second half. I should take these items that come after I to the left. And then manipulate j and n appropriately so that things work. So if I'm shifting to the right, j has to increase and n has to decrease. If I'm shifting these guys to the left, then only n has to change. J doesn't have to change. Okay. So we can quickly take a look at what that code looks like. That is array dec. So here's for instance, the add operation. First check for out of bounds conditions, then check if you need to resize. Then if I is less than n over 2, you're going to shift these things to the left one position, meaning you're going to move them to the left to make one extra space. And that's just a for loop that counts starting at 0 and going backwards, or sorry, going forwards. Otherwise, if you're in the second half, you do a shift to the right. That's this other for loop. And finally, you've cleared position j plus I. You set it equal to x, and you increase the value of n. Notice that in the first case, we also had to change the value of j because we are shifting this one position to the left, meaning j has to be decreased by 1. Okay. And this line of code here is basically implementing j equals j minus 1 modulo the length of A, except that I remember I said we have to worry about negative numbers. So we do it just by checking if j is equal to 0. That's the only weird case. Then we set it to the length of A minus 1. Okay. All right. And remove is the same thing. There's a branch here, whether I is less than n over 2 or bigger than n over 2, and we shift appropriately. Now, two questions, or maybe one question. In the fast array stack implementation, we used system.arrayCopy instead of a for loop to make it faster. Can we do that here? No. We can't do that here because we're simulating this circular array, and system.arrayCopy knows nothing about what happens when you go past the end of the array, except that it should crash. So system.arrayCopy is not an option here unless you do a lot of casework. And the last thing I just want to show you is, does this really work? Does this make anything that is fast? So let's test this array dec. Okay, So ArrayDec did its million Q operations in 0.037689 seconds, and ArrayList is going to take, I don't know, 10, 20 minutes to do the same thing. Okay? So this isn't just some theoretical thing that's, doesn't affect anything. This is the difference between 0.03 seconds and however long this is going to take. So that's it for today.